Ronnie, and folks, good morning and thanks for, or good afternoon and thanks for being with me today. I would like for for you, if you can, to stop multitasking for the next hour. I'm gonna introduce you to the basics of space communications. But as you know, everything is space. In space is so difficult that space communication 101 might be like 301 in any other area. So bear with me. But at the end of the hour, I think you're gonna know more about the space communications than 98% of the population out there. So I think it's gonna be a good investment. So before we go into the details, let me do a very quick introduction about myself. So me a little bit better. My name is Alberto Montilla. I'm a founder and CEO of SPATIAM Corporation. We are a small startup with the mission of creating the interplanetary internet and becoming a leading service provider. I'm also a board member of the Interplanetary Networking and Special Interest Group, that's IPNSIG within the Internet Society. And I accumulated more than 25 years of experience in communications and networking services. I also have been a professor in my early career of specifically on radiation and propagation. And you're going to hear a little bit about that during today's background on space communications. And I'm also, in terms of education, I'm a PhD or I have a PhD on networking engineering, as well as an MBA, and my background is on electronics and communications as an engineer. So with that being said, let me set the agenda for today. We're going to start with, I want to make it as practical as possible. So we're going to start with defining an extreme example of a space communication. So that's basically as hard or as far as it can go. Then I'm going to talk about something very important, the foundations of space communications, or why space is different. Then we're going to talk about how space or the problem can be segmented into smaller chunks, and also how NASA approach it. That will give you an idea of what things are happening and going on. And then we'll go into building a space network. And when I talk about network, I'm not only talking about the networking layer, but I'm talking about the whole thing. So physical layer, the space link applications, and then we're gonna go into data transfer, and we're gonna end up with a space networking and talk a little bit about that, okay? So let's start with my extreme example, and this is Voyager 1. So this is the first human-made object reaching interstellar space. So that's the object that we as a humanity have made that is farther from Earth. It was launched in 1977. So I'm sure that many on these calls, were not even conceived or thought of being conceived by the time. If you think about 1977, internet didn't exist by then. Data communication was something just starting. But NASA is NASA, and they were able to put this out there. It's still flying, still sending data. It reached interstellar space in 2012. What that means is that it left the influence of the solar systems. It's the first object that actually left the solar system. Now there are two, Voyager 1 and Voyager 2 are in interstellar space. So let me give you some ideas of some of the topics I'm going to talk about through this example. When we look at physical aspects, think of the following. Voyager 1 is at 14.3 billion miles from Earth. So don't even try to picture it. It's a lot. It is moving at 37,000 miles per hour. So it's faster than anything that we have been able to put out there. And one thing that is mind-blowing, and it's central to what we're going to be talking about today, is the fact that speed of light, or the time it takes for light to go from Earth to the spacecraft, is 21 hours and 26 minutes. What that means is that if we send a message, any sort of message, and let's say in a radio wave, it takes 21 hours to get there. Now think about the following. any conversation, any human conversation that takes more, that has more than 400 milliseconds of delay, it's considered to be, not a good communication, because the delay is so big, and this is only 400 milliseconds. That is not good to have. I'm sorry, there is some noise here. So there is the delay is so big that beyond 400 milliseconds it's hard to have a conversation. So for those who have used had a phone call over satellite, that's a challenge. Now imagine 21 hours. So it's impossible to have a phone call there. But not only that, if you have to send a message, let's say a ping message, it takes almost close to 2 days to get a response back. So you have to wait for 2 days to see if the ping is successful, which defeats the purpose, right? You send a ping because you want to know almost immediately that something is going on. Now, some communications attribute about Voyager. It communicates on the microwave band, bands. They have two bands, X band, which is the 8 gigahertz, which is the one that it's currently using, and then there's an S band that is currently off because it was set off many years ago. The signal level received on Earth, it's 1/10 over 16 watts, so basically nothing. And we have antennas in the Deep Space Network, I'm going to talk about that later, that are able to receive that such a low power or such low energy. Let's talk about how difficult it is to send and receive data in space. And then the other thing that is curious is that the current bit rate is 160 bit per second. So compare that with the 300 meg or the 1 gigabit that you have at home every single day and every single time. So that talks about the fact that you have to be extremely efficient in how you code and send data through space. And also I'm going to talk about why it is 160 seconds, 60 bit per second instead of 2 gigabit per second. So there is a NASA being NASA, there is a lot of information available. So for anyone who is curious about Voyager and more details, you can go to voyager.jpl.nasa.gov, and you can spend hours and hours and hours getting fascinated by Voyager. So let's talk about some of the foundations and why space is different. So physics is physics. So the physics of space are not different than the physics of what we experience on Earth. What is very different is the fact that in the space, the volume of a space is of a dimension that is very hard to grasp. So let me give you some ideas, right? What we call the Earth vicinity. So anything that is very close to Earth, let's say all the way to the moon, we're talking about hundreds of miles. So for example, you talk about the low Earth orbit, this is in the hundreds of miles. Then if you go to the the farther orbit, which is the geostationary orbit, you're talking about tens of thousands of miles. And then when you go to the moon, you're talking about hundreds of thousands of miles. So this is Earth vicinity. But then when you think about the solar system, you're talking about hundreds of millions of miles. So, you need to multiply the number above by another 100. So, think of, Mars, which is between 35 to 250 million miles, depending on the time of the day. That distance changes every 2 years. Or if you think about interstellar space, so basically leaving the influence of the sun, you're talking about billions of miles. Just to give you an idea, the closest star is, and you have the number there, it's something around 4 light years, which equates to the number down there in kilometers, 40. I think it's trillions, right? 40 trillion kilometers. So it's just too much. So what effect do these distances have in the communication delays? So let's look at it quickly. If you're in the Earth vicinity, your delays are in the milliseconds to seconds. If you are in the solar system, your delays are between minutes and hours, or minutes to hours. And if you are in interstellar space, your delays are days to years. And again, these communication delays have to do with the speed of light. You know, Einstein told us that nothing can travel faster than the speed of light. That's true, at least, you know, till today. So any wave you send, whether it is optical or radio, it's gonna be governed by a speed of light. So, and the speed of light move at 300,000 kilometers per second. Then, you know, you make the math and you get those communications delays. And the reality is that, you know, we haven't discovered yet the multiverse or anything like that. So the only thing you can do with this is to wait. There is nothing else. You send a message, you send a radio wave, a signal, and you need to wait, depending on how far the other end is, to get a response. The second big consequence of distance is signal loss. And again, this is signal and communicate, well, more than communication, signal theory, which is the signal power or energy will, or power will decrease with the square of the distance. And it also depends on the frequency. So at microwave ranges, you're talking about that, you know, you're gonna lose, and you have the numbers there. We use a logarithmic, the numbers get so big or so small, then we use logarithmic notation. That's decibels to express gain or loss. And, you know, if you are in the Earth vicinity, you lose between 150 to 230 decibels. That's a lot. Then, you know, as you go down there, you know, you see, you know, you're losing, you know, 10 at minus 38 in power. So what that means, how do we overcome that? Well, the way to overcome that is you transmit more power, which, you know, if you are on Earth, that might be possible because you have energy, you have, you know, possibilities to, you know, have bigger antennas. However, if you are in a space where you're running on batteries or solar panels, you may not draw all the power you want, so you might be limited there. B, larger antennas, because there is a dependency on, especially for microwave frequencies, there is a dependency on the size of the dish and the gain it has. So the bigger the dish, the larger gain. So the largest antennas we have right now on Earth are 70 meters antennas. These are the NASA Deep Space Network, the European Space Agency, and also the Russian space agencies. They have also, you know, Deep Space Network capable antennas, very large antennas. But then again, the same thing. When you look at the spacecraft, there's going to be a limitation there. You cannot put, you know, the antenna size you may want. So the way to mitigate signal loss is by having larger antennas, better amplifiers, better receivers. What that means is money. You need to put money on the table to, you know, have better and better. Just to give you an idea, the amplifiers and more than the amplifiers and the receivers, and the receivers are in cryogenic cooling, so they run maybe 10 or 5 or 4 degrees over absolute zero in Kelvin. And that's expensive. And the reason is that, you know, there is this is thermodynamics. There is a relationship between noise and temperature. So the lower the temperature, the lower noise you're going to introduce, then, you know, the better possibilities to receive the signal. So first thing that is very different in space is space itself, is distance, okay? So the second thing, and I'm going to illustrate it through an example, is disruption, which is, you know, in order for two endpoints to communicate to each other, you need to have, especially when you think about radio or optical waves, you need to have line of sight, which is you need to see each other. In space, that's not always possible. So let me start with an example, and then I will explain the logic.
What happens when the sun blocks our signal? About every 2 years, Earth and Mars wind up on opposite sides of the Sun. That's called solar conjunction. It's like being on either side of a huge bonfire. We can't see Mars, and our landers, rovers, and orbiters can't see us. If our spacecraft send back signals, charged particles from the Sun could interfere, causing gaps in the data that reach us. That's not a big deal. If something's missing, it can always be resent later. But no way do we want to lose data when we send up commands. Receiving a partial command could confuse the spacecraft, putting them in grave danger. So mission controllers plan ahead by sending up simple to-do lists, including regular health checkups. Back home, this break in communications lets team members catch up on other work, or take a well-deserved vacation. Solar conjunction lasts just a few weeks, then it's back to the grindstone, on Earth and on Mars.
Okay, let me tell you a curiosity. Right now, we are in solar conjunction. So it's a process that happens every 2 years, and they last a week and a half to 2 weeks, and that's happening right now. So for those who have an Apple Watch, they have one of the skins that have the solar system, and you would see Mars and Earth opposite to each other respect to the Sun. And it's true. You look at NASA, you look at their, they publish their communication plan, and during these years is all about trying to get telemetry, but don't touch the rovers, because you may have the side effect. So what this creates is the following. In order to avoid disruptions, you need to have coordinations. So disruptions have to do with celestial mechanics, which is, again, I was telling you that for two endpoints to communicate to each other, they need to have line of sight. Now think of the fact that planets, things, they rotate. So they may be looking, they might not be looking at each other. They also translate or move around. They have moons, there are solar conjunctions, there are many, many things. So space agencies have looked at ways to manage disruption. So let me give you another quick example, because I think it's going to illustrate the complexity of the coordination.
After 7 dramatic minutes of entry, descent, and landing, everyone will want to know, did Curiosity survive? There's a possibility we won't know, at least not right away. During its descent through the atmosphere, Curiosity must switch to a new antenna for each transformation it makes. At each switch, we could lose lock on the signal for a short time. That won't hurt the rover, it just means we won't know what's happening right away. Even with a solid signal, the communications link direct to Earth only works during the first half of the rover's descent. Why? Like Earth, Mars is spinning, and during landing, Curiosity and its landing site will disappear from view like the sun setting. Out of sight equals the end of direct radio contact. But NASA has 2 spacecraft orbiting Mars that can help. For the second half of Curiosity's descent, the Mars Odyssey orbiter is in a good place to pick up the rover's signal and send it right back to Earth. To best hear Curiosity's signal, Odyssey must rotate about an hour before landing. That sounds easy, but engineers are asking Odyssey to perform a maneuver it's never tried before. Will it work? Probably, but it's not a sure thing. If Odyssey doesn't rotate successfully, never fear, the rover won't be affected whatsoever. Once again, it just means we have to wait longer to hear from the rover. Odyssey could perform as hoped, but we're still not home free. Engineers always think of what-ifs. For instance, what if the rover lands on a slope? If so, the low-flying Odyssey orbiter might not be able to pick up its signal. Even if everything goes according to plan with Odyssey, there's a final challenge: time. The rover may be standing safe on Mars, but Odyssey has to be quick in getting the signal. Odyssey is moving fast. It will only be in the line of sight to hear from the rover for a few minutes, perhaps no more than 5. So the Mars Reconnaissance Orbiter plays the role of backup. It will also fly overhead to capture what happens and then store the landing data it collects on board for playback to Earth a few hours later. Engineers then have to decode the data, which takes several hours. Sometime in the middle of the night for Curiosity's mission team, it's possible that the orbiter could tell us the rover's fate. Or there are other scenarios where the rover might be perfectly safe, but we might not hear from it for 3 days. That's all to say, Curiosity's landing is filled with drama and will need lots of patience. No wonder they call this rocket science.
Okay, so this video was a little bit more complex and introduced a couple of items which I'm going to try to explain here. The first one has to do with the concept of a relay satellite, and that's nothing else than, in the case there is no line of sight between the two elements that want to communicate, you introduce a third element, which basically allows you to do the communication by having this relay. So one key example, and this is one of the things, most sophisticated things that NASA has in their near space network, is their TDRES, which is Tracking and Data Relay Satellite. This is a network of satellites that are in geostationary orbit, that all they do, as the name indicates, is to relay data between Earth and items that are in the low Earth orbit. So for example, the International Space Station. So because the International Space Station is not in geostationary orbit, so it's moving around the Earth, not in synchronous mode or in asynchronous mode. So the way to achieve, for example, communications from their White Sand complex to the ISS 24/7 is to using the network of relay satellites, and that's how you can achieve certain speed, and that's how you can achieve with moving objects. It also serves, for example, the Hubble Space Telescope, and it also provides support for any or majority of the rocket launches out there, because as the rocket is going through low Earth orbit and beyond, then the way to communicate and keep communication is to the relay satellites. So these relay are a little bit more complex because these are communication satellites. These are not science satellites. Their purpose is just to repeat this, let's say repeat data. But when we say repeating, these relays may be supporting multiple frequencies at the same time, because the spacecrafts might be supporting, microwave frequencies. The assets on surface, for example, on the Moon or Mars, might be supporting ultra high frequency UHF, and the role of the relay is also to the conversion of frequencies. So there are relays operating in they could operate in any orbit. So for example, TDRES operate in geostationary orbit. The two relays of the previous example that are in Mars, they operate in Mars low Earth orbit. What that means is that they are moving from a stationary object on Earth. Those satellites that are not in geostationary orbit are moving. So this introduces the second concept, which is the concept of the contact. Contact is the time or the period in which two objects have visibility, therefore can exchange data. And that visibility can be direct or can be through a relay. So for example, in one experiment we did earlier this year in low Earth orbit, we were talking to a satellite, and the contact window was literally 4 minutes. So imagine the amount of coordination you need to have, because you need to ensure that whatever data you're going to send it during 4 minutes only, and then that 4 minutes are going to repeat every 90 minutes, every 89 minutes, depending on where the satellite is specifically located. So celestial mechanics, which is the famous n-body problem, rotation, translation, conjunctions, etc., causes disruption because there is no line of sight, at least on a permanent basis, which means loss of communication. And the way to solve for that is to expand the coverage. First on Earth, the way to ensure that as Earth rotates, there is always a communication antenna is to use the famous 120-degree separation. which is you have a minimum of 3 antennas separated at 180 degrees, and that way you achieve global coverage, at least from the equator perspective. Then from the space perspective, and let's focus on the Earth vicinity, then is having a satellite network. So if you are in geostationary orbit, what that means is that the satellite doesn't move to a specific, relative to a specific point on Earth. You only need 3 satellites, or a minimum of 3 satellites if you're in geostationary orbit. And if you go down from there, you need more satellites. You know, on MEO, you might need, on the medium Earth orbit, you might need 10 or 12. Then if you go to LEO, you might need 50 and above, depending, the area you want to cover. GEO have the advantage of it's geostationary, but the GEO orbit is at almost 36,000 kilometers. So what that means is that you need more expensive satellites because they need more power, because there is larger distance, there are larger delays. So what is happening right now, and that's where you see all these Starlink constellations, or the Starlink constellation from SpaceX, or the Kuiper constellation from Amazon, and many others, they are placed in low Earth orbit. What that means is that you need a lot more, especially if you want to cover the entire Earth, you need to have a lot more satellites. However, each satellite is going to be less expensive. So it's easier to transport there, to deploy. And then if you have to replace them, it's lower cost. So now there is this big approach into, conquering the low Earth orbit. It's called LEO, as a the term. So it's LEO, MEO, or GEO. And then for certain type of satellites, and this is not necessarily for communication, but more for science satellites, there is other type of orbits, like the highly elliptical orbits that are used. There are also satellites that have polar orbits, because you want them to cover, the poles, which, the typical geostationary satellites and even LEO satellites don't cover. So because they need a very specific way of getting into orbit. Okay, so we look at the 2 big factors in the space foundations, distance and disruption. Now let's have a quick look at the spacecraft constraints, which is when we are building a spacecraft, could be a satellite, it could be a rover, anything that flies to space. What kind of constraints you have? And there is a term named SWAP. That's the term used in the industry, which means size slash space, weight, and power. These are the 3 things that are always going to be constrained. First, because this stuff has to be transferred by a rocket. You need escape velocity, and what that means is that the bigger it is, the harder it is to get into a transport spacecraft into a rocket. The heavier it is, the more fuel you need, so it's going to get much more expensive. And then the more power it consumes, either you need to have more batteries, more expensive batteries, or you're going to have a shorter lifetime, which is very important. So think of Voyager. Has been in space for more than 40 years, or now getting close to 50 years. If you have a large consumption, then there is no way any mission would survive that long. So these are the constraints, and these constraints, for good or for bad, they affect the communication design as well, because if you need to have a small form factor, the first thing that comes to your mind is antenna size. How big can the antenna be? And depending on that, how much gain it's going to have, and depending on the gain, how far it can communicate effectively, or also how many bits per second can you put in, because you may need to put more coding into it. Same thing with weight. It would reduce how much computing you can put in. It would reduce, every single element has to be done, built as light as possible. And the same thing with power. It also has to do with, that there is a term of energy per bit that depends on the communication technology you use. So every bit that you are transmitting or receiving consumes power. So there are limitations on the bit rate that are simply put there to save energy. Okay. So, given that space, space challenge, one thing that agencies and academics have done is to split or segment space. And the reason to do that is trying to find segments in which things don't change much, so that you can design based on those specs. So you already talked about LEO, MEO, and GEO. So this is low Earth orbit, medium Earth orbit, and geostationary orbit. This has been very traditional nomenclature to define where satellites are going to be placed. And based on that, you need to have certain specifications of power, number of satellites, etc. And then you have everything outside that. The way NASA has divided that is currently is there are two networks supporting space communications. The first one is the Near Space Network, and it covers anything that is moon and internal to the moon. Okay, low Earth orbit, MEO, GEO, and also cislunar operations, which is anything that happens between Earth and the moon. And then there is another network that it's named the Deep Space Network. And these are the very, very large antennas that communicates to everything all the way up to interstellar space. So you would find, if you go to NASA.gov and look for SCAN, which is their communications and navigation department, you would find quickly that there is a Near Space Network and the Deep Space Network. The interesting thing, so that you know, is that the Deep Space Network is managed by the Jet Propulsion Laboratory, JPL, and Near Space Network is managed by Goddard Space Flight Center. So as you may imagine, there is a lot of coordination between them. So very quickly on this is the quick map of NASA Near Space Network, NSN. And what you see are all the ground stations that are around the world supporting all the assets, all the missions that are in near space. It's all, it's primarily based on radio. Now they have added optical. I don't think there's a picture here, but they have added a couple of optical stations as well. One is in Hawaii, and the other, I don't remember where it is. And the other thing that is very interesting is that they also have commercial partnerships. So a couple of these stations are commercial stations. So these are commercial companies that have ground stations, and NASA has partnered with them. So for example, I know they have partnered for communications on the poles. There are companies like KSAT that have a good network in the Arctic. So NASA have partnered with them, and NASA uses their network. And then the thing that you see on these blue squares are the TDRES satellites. So these are the satellites that are in geostationary orbit providing services to near space. Now, this is a vision of the Deep Space Ground Network. So they have three sites. Remember the 120 degree problem. So they have one site in Goldstone, one site in Madrid, and one site in Australia. Each site has many antennas. The most famous antennas are the 70 meter antennas, and that's just because they are extremely huge and extremely expensive to build, to manage, to operate. They have been around for many, many decades. They have slowly added other type of antennas, and now the most modern antennas are the 34 meter antennas. They use a slightly different technology to reduce cost and maintain the same gain. It's a beam guided. That's antenna technology. I won't enter there. But basically, what they do is that they monitor they have a schedule of contacts for each spacecraft, and depending the time of the day, depending the maintenance, their operations, the spacecraft would connect to one of these antennas at a time, and then they have a ground optical network to basically, get the data to the point it has to go, it has to arrive, and we're going to talk about that in a second. Okay, before I continue talking about building a space network, any questions so far? Any comment?
Nope, not for me.
This has been great, Alberto. It's very informative stuff. I really appreciate you taking the time to go over all this.
Good. So if there are no questions, let me now go to building a space network. And the beauty of these, folks, and for anyone who is interested into digging deeper, is that all this information is public. Remember that NASA is a government organization, and because of that, all the information they produce, unless it is for national interest or security, all the information they produce is public. So there is an organization named Descanso. It has a Spanish name. Don't ask me why. I don't know the story, but Descanso is responsible for documenting, and they have extraordinary system engineering books. So they explain how they design the communication link for the Voyager, for the Mars Curiosity, for any major mission. You find all the info there. It gets super technical, but as you go to 1, 2, or 3, you get to understand how they do it. So the first thing is, when you build a space network, is the space link, the physical layer. And why? Because without the physical layer, there is nothing else. As you know, if you look at the OSI layer, it's physical, it's a link, it's network, transport, and then you go to presentation and application. So everything sits on top of the link layer. And this is done through something called the link budget, which basically at the end of the day, you need to ensure that there is, for a given communication link of two objects that are going to set apart at X distance using X frequency and X coding technology, the antenna is going to receive a specific signal level, because that's the threshold in which, according to information theory, you're going to be able to decode the data. And as complicated as it sounds, it's pretty basic math. It's a series of multiplications and divisions, and as we use logarithmic, or we turn this into a logarithmic equation, it's basically sum and differences. That's it. You start adding up and subtracting. That's what it is. Things that add up, it's the transmission power, the antenna's gain, both the transmit antenna and the receiving antenna, and things that subtract are the free space loss, which depends on the distance and the frequency, the transmitter loss, which is, for example, the loss that is incurred on the cable that goes to the antenna, from the transmitter to the antenna, and other type of loss that has to do with temperature, polarization, other stuff. So basically, the whole thing is about the fact that there is a minimum signal level that has to be received for the system to be able to demodulate and get the data. And this depends on the specific encoding and the specific modulation. So for every mission, or every link, that's the first thing you are going to do, because that helps you to design or at least understand how far you can go, with a specific set of equipment. And you have to do this for each specific link, okay? So some notation is, from Earth to the satellite is uplink, you're going up, and from satellite to Earth is downlink, because you're going down. So how does this look like? And this is real. This is what's taken from a NASA report. This is an analysis they did for a communication link between a satellite and a specific antenna in Stanford University. using ultra high frequency link. This was for a test they did from Mars. And what they do is basically collecting information. This is the modulation, the transmit power, the losses, all the miscellaneous losses, and you start adding up to see if you're going to be able to get enough energy to basically decode the data. And they do this all the time. As I said before, you have the link there. I'll distribute the slides later if you want to look at that. So now let's look at data transfer. Okay, so we look at the link and we assume that at the physical layer, we are able, and including link, little bit of link layer, because of the coding, we are able to receive data. Now let's try to understand what type of data and how typically this is looked at. So there are primarily 3 types of data. I put here 4 because one is very specific to the use case. But in general, if you look at any mission, the first thing you have is telemetry. Okay, telemetry is any data that you get from the spacecraft to Earth. This could be science data. So, for example, a spacecraft may have a plasma detector or X-ray detector, and you want to know the levels. And the sensors gather the data and then put it down on the downlink. Gets to Earth, and that data is processed by scientists to understand, a little bit better the universe. There is engineering data, which is basically data about the sensor itself, the temperature of the sensor, the levels of the buffers, etc. That's just to ensure that the mission, the mission is running with quality, or just to understand how the different elements, for example, battery life, is a critical one. And then within telemetry, one specific area that is growing in popularity, especially near Earth, is imaging. Pictures, videos, that also gets there. The second type of data is command, which basically command is control functions that go from Earth to a spacecraft. And that's basically telling the spacecraft to do something. And it could be something with their sensors, or it could be something with the operation itself, like, go to backup, something that happened with the Hubble telescope, a couple of months ago. Started failing, and, they rerouted the whole thing to the backup hardware. So these are commands. The third piece, which I won't talk much about it because this is for this deserves another full session, is tracking and navigation. So we all have Google Maps or Waze, and we see how easy it is. It depends on GPS. Well, in space, especially when you think about deep space, there is no GPS. So how do you know where the spacecraft is, and how the spacecraft knows where Earth is? And it might be trivial, but it's a very, very complex problem. So the beauty of communications and radio communications is that you can use the same communication radio waves to help both the spacecraft and the ground system to position each other and to understand where they are. And if you know where you are, then you likely know how to navigate. This has to do with it's deep physics, Doppler effect. So you can demodulate the signal and basically know your speed and where you are going. So that's a big in space. You use the same signal to being able to do navigation and tracking. And the last one, and that's very specific to building an internet, for example, is communications. I talk about TDRES, the relay satellites. So there are satellites that are built just for the purpose of enabling communications. So they don't have science, they don't have anything else. They just move packets or data or signals in and out. So that's for this type of satellites. It's not about telemetry. It's not about it's how you carry data from other elements. So on the table below, what you see is typically the direction they have And also something very important, the volume of data. So for example, telemetry, if you're talking about video or images, there's a large volume. You're talking about megabytes, gigabytes. They may have quality requirements very high because you need to ensure that the data is accurate, but you may not need to receive the data right away. You may hold on that data until it is the right time to send it. However, with the commands are very low in terms of volume because the command might be, move to backup or, turn the antenna around. However, the quality requirements are very high, both in terms of timing as well as accuracy. Why? Because you need to ensure that this is going to be received in the right order. The command, has to be the right one. Tracking and navigation, same thing. Volume is very low because these are carrier signals for the most part. However, the quality requirements are very, very high. Requires very high accuracy. Why? Because you need to know where the spacecraft is. Otherwise, get lost. Bye-bye. You lost billions and billions of dollars of probably on that mission. And then in terms of communications, volume is very high and quality is very high. Why? Because you are typically carrying data of any type. You're going to carry command data for other spacecraft. You're going to carry telemetry data for other spacecraft. So communications, satellites or spacecraft have a very, very high requirements, which also talk about the hardware capabilities. So we look at the physical layer. We look at the data and the type of data to send. Now let's have a quick look at the protocol stacks and think of the following. Protocol stacks have been built together with, the evolution of space exploration. So as you may imagine, there is not a single protocol. There is a suite of protocols. Some of them are more legacy because they were built years ago. Some of them are newer because, they have been built for what is coming next. So what I'm going to be focusing on, it's on those that are very popular right now. Okay. So first, if you look at the left-hand side, the bunch of boxes there, you see the typical OSI layer, physical layer, link layer, network, transport, and application. And then you see a series of protocols. They have been designed for different type of applications. So for example, right here, I don't know if you see my mouse, but right here, you see the proximity one protocol. This is a data and physical layer protocol designed, as the name indicates, for short distance satellite links. Okay, and it's built over a specific set of frequencies. Then on top of it, you have a network layer where you have IP. IP is always there, and we're going to talk about that in a second. And then you have the Space Packet Protocol, which is an encapsulation protocol. Okay, it's a Space Packet Protocol. For those who know about networking, it's more similar to MPLS than anything else. It just helps encapsulating and provide a standard layer. And then on transport, TCP/IP, and then you have specific conversion of TCP for space. And then you have the famous CFDP, which is the CCSDS file delivery protocol. So CCSDS is the Consultative Committee of Space Data Standards. It's a standardization body that is formed or was formed by space agencies. So they basically hold ownership for what is standardized, and typically space agencies participate in the standardization and at the same time adopt those. As you may imagine, CCSDS is not standardizing TCP/IP, and many other protocols. What they do is that in their specifications, they say, hey, we standardize TCP, we're going to use TCP/IP for the spacecraft in a very specific way. Okay, and then you have the application protocols for, for example, data compression, for images, for other stuff. So how this is represented in a typical application? Well, look at here on the table on the right. That's basically a satellite station, an Earth station, and a relay. And this is for sending telemetry data. So it uses the CFDP, which is very good for file transfer, sending telemetry data from a satellite to Earth. It uses the CFDP protocol on top of the Space Packet Protocol, on top of the Proximity Space Link Protocol, and boom, you're able to transmit data from A to B through a relay. So this is how many missions have been done in the recent years. CFDP is a protocol that has been adopted, standardized. It's a file transfer protocol. It also provides for store and forward mechanisms so that you could have even a CFDP relay. CFDP is very good when you think about communicating on Earth vicinity. The moment you have many nodes, the moment you want to transmit big chunk of data, CFDP falls short. And I won't enter into a lot of detail, but because of the limitations of CFDP, around 10 years ago, agencies decided, especially NASA and JPL, decided to engage into a new networking approach, which is DTN, delay and disruption tolerant networking, in the form of the bundle protocol. Okay, and the bundle protocol, before entering into the details of what it does, it addresses certain limitations of CFDP. The first one is networking. CFDP was built to be a point-to-point application protocol. What that means is that I'm sending from A to B. With disruption tolerant networking, or the bundle protocol more specifically, you have a contact plan that allows you to go from A to B through multiple paths, similar to the internet, very similar. So instead of having a routing table, you have a contact plan, but it's pretty much the same approach. Why do we need contact plan in space? We already talked about disruptions. You need to ensure that you are communicating with the other end at the right time, and that's a contact. So instead of having a routing table, you have a contact plan. The second thing is that on CFDP, the unit of communication was the file, the entire file. So for example, on CFDP, if you were doing a store and forward, you first had to transmit the whole file to the relay, and then the file would be relayed back to the point B. That works nice well for small files. It works pretty bad for big files. So what the bundle protocol does is that it works with the concept of a bundle, which might be a much smaller segment compared to a full file. And a bundle similar to TCP/IP might be configured based on the underlayer MTU. Then it has better data handling for network efficiency. So for example, it has time to live, similar to IP. What that means is that if the bundle has been there for too long, it just gets deleted, not consuming memory, and then the node will be available for other type of communications. And then it has other type of services such as streaming, multicast, etc. So it's not only for transferring files, but for transferring messages and other type of data. And the way it works, and look at this picture here, the way it works is that BP, analogous to TCP/IP, BP becomes the networking layer. And you can have other transport protocols, other link protocols, depending on the type of link you have. So if you're in a terrestrial network, you're going to use TCP/IP. Why not? On the bundle protocol. However, if you have in deep space, TCP/IP simply don't work because the delays are too long. So you need something else. In this case, you use the link glider transmission protocol, LTP, which provides reliable transfer over space, deep space links. So BP becomes that networking layer that allows you to adapt the underlying layers based on where you are, terrestrial, Earth vicinity, or deep space. So more details about the bundle protocol, and many of you know this already. In terms of a model, the bundle protocol have its agent that basically is responsible for the bundles. It has a storage, because remember, this is a store and forward protocol. So it would store any bundle that it has custody for. And then it has an application agent, which basically have the northbound interfaces to the applications. And then it has convergence CLAs, convergence layer adapters, which is, under the bundle protocol, you may have TCP/IP, or you may have LTP, or you may have UDP. So each of those are a very specific adaptation layer, which, in these terms is a convergence layer. Then in terms of the bundle structure, so the primary unit for the bundle protocol is the bundle. Same thing that for the internet protocol for IP is the packet. In this case, the name is the bundle. And the bundle is formed by a series of blocks. There is a primary block that is basically the header and the options. Basically, the primary block tells you, the characteristics of the data. And it tells you things such as the address, the lifetime, whether you're asking for custody or not. So it tells the receiving end, details about the information that comes next. Then the payload block is data. The payload can be as big or as small as the implementation decide. Typically, this governed by the convergence layer. So if you have an MTU of 1500 bytes, you need to know that the whole thing cannot be bigger than 1500 bytes. So then there could be bundle fragmentation in this case. And then there are optional blocks for things such as security and other protocol options as well. But these is a very, very standard approach. And the bundle protocol, as you know, there is an RFC 5050, which has standardized bundle protocol version 6. And now there is a draft that is very mature. It's in the process of getting to RFCs in addition now, that specifies bundle protocol version 7. There are quite a few bundle protocol implementations. Just from NASA alone, there are 4 implementations right now. The most complete one is ION. Its name is Interplanetary Overlay Network. This was done by JPL, very specifically for deep space. Then there is the bundle protocol implementation on CFS, or flight software. So this is the operating system for spacecrafts. For example, this is the operating system that is in the ISS. It's the operating system that is going to go on the Lunar Gateway. And it has a library for the bundle protocol. Then there is DTN Marshall Edition. And one that is very new, that's from Glenn, is the high-speed DTN codec. I won't go into a lot of detail, but this is very interesting because one of the feedback from the experiments done on the ISS with DTN is that at some point of time, DTN becomes a blocker. You need to get DTN in hardware or simplify the bundle protocol to be able to run at very, very high speed. So there is an implementation that look into that, simplifying the protocol, not the protocol, but simplifying the implementation so that it can truly go at very high speed. The European Space Agency also have an implementation. That implementation is not available yet publicly. That's the ESA bundle protocol implementation. Is a Java implementation, and the rest of the implementations are built on C code. And then there are a couple of there are a few commercial implementations. Micro D3TN. This is probably of the commercial implementations the only one that has been tested in space. This is from the company of the same name. They are based in Germany. It was originally designed for very low computing footprints, so more of microcontrollers type of implementations. And then there's DTN7 and other type of, and there are others that have been built primarily for DTN on Earth, and which, it's another implementation, is basically delayed tolerant networks in Earth challenge networks. Now, what is happening out there? What is happening is that space agencies, companies are now working heavily to ensure that we continue building the interplanetary internet. So some people term it the interplanetary internet, some other term it the solar system internet. It's the same thing. And it basically covers 4 main areas right now, where there is a lot of activity. First, anything happening close to Earth. Second, the moon, then Mars, then asteroids, and then we can talk about some of the missions that NASA is doing in deeper space. But the bulk of the activity is happening in those 4 areas. So on Earth vicinity, there is already a bundled protocol implementation on the ISS. There are other missions going out starting next year that are going to be based on delayed terrestrial networking. Then moon, for the moon, what is happening is the Artemis missions. It's already agreed that the gateway is going to be DTN enabled. The NASA network for the moon is called LunaNet, and that has both TCP/IP and the bundled protocol as the networking layers. Then for Mars, there have been experiments using DTN already. And there are missions like the Psyche mission that are also going to be testing DTN. There is also a mission to Mars, I believe, from the Korean Space Agency, where there is also going to be DTN testing, or not DTN testing. They're going to use DTN for the communication as well. So at space speed, think of it that we're going to be back to the moon very likely in 2025. We are going to go to Mars somewhere in the 2030s. So the interplanetary internet is going to be built according to human and economy in space. So let me show you an example, and this is a very concrete example, LunaNet. Before I show you the example, one thing I want to highlight is we haven't talked much about it. Is you may wonder, why don't we use TCP/IP everywhere? It's the foundation of internet, and I would agree with you if it was not for the fact that TCP/IP as the networking layer doesn't work in deep space. As soon as the delay is beyond a few seconds, the 3-way handshake that TCP uses simply breaks, because you need to basically do 3 handshakes before you can send the first packet, and the sliding windows mechanism of TCP also breaks. So the moon is right there at the border. The delay to the moon is one-way light delay is 1.3 seconds. So it's right there. So for example, if you have a direct link, you may have a TCP optimized for space, and that could work. But if you're in the dark side of the moon, going through a satellite relay, the delay may go all the way to 2-3 seconds, and that's where TCP breaks. Because of that, both bundled protocol and TCP/IP are options for the moon, for LunaNet. But then when you go to Mars, which is the next step, is all about the bundled protocol, because TCP/IP simply doesn't work. So with that being said, I'm going to run a quick video to show you what NASA is doing for LunaNet, and it's something I'm very proud, because we are actively commenting on the standardization of the protocol, and more specifically the standardization of this network.
LunaNet, enhancing connectivity and empowering missions at the moon. With LunaNet, NASA's science and exploration missions will be more connected than ever before. LunaNet will offer users robust services in networking, navigation, detection, and science investigation. LunaNet will bring internet-like capabilities to the moon through the use of delay disruption-tolerant networking. Users will be able to access the network through multiple nodes, connected with others on and around the moon, similar to our use of Wi-Fi and mobile networks on Earth. For navigation, missions using the network will have access to location and timing signals, enabling astronauts and rovers to traverse the rocky surface and find their way back to base. And while on the moon, it is essential for astronauts to know when to prepare for an incoming hazard, such as a solar storm. LunaNet will relay this critical information through its detection services. Using enhanced instruments and networking capabilities, astronauts, rovers, and orbiters can be forewarned about incoming storms, that bring increased radiation to the moon. Using the navigation aids provided by LunaNet, these assets can seek shelter. LunaNet also allows for investigative science, which will lead to new discoveries and deeper knowledge of our closest planetary neighbor. Using LunaNet signals, NASA can also learn more about communicating in space and plan for future voyages. LunaNet directly supports NASA's Artemis program, which plans to land the first woman and first person of color on the moon and establish a sustained lunar presence. The Artemis missions can leverage the LunaNet architecture to ensure connectivity and safety. LunaNet is comprised of multiple nodes, each capable of providing some level of the different services to form the larger infrastructure. A user can get network access through one node, which will then relay the data through multiple nodes until the data reaches its destination. During this, the user can simultaneously be receiving data and alerts from the network. The architecture allows NASA, commercial, and international partners to team together to answer the challenges of deploying a robust and high-performing infrastructure. Working with partners, LunaNet will quickly expand into a flexible and interoperable architecture and become extensible to Mars and beyond. LunaNet is the first step in creating the solar system internet and will keep explorers connected to Earth. The priority for our journey to the moon is discovery, learning how to live in space so that one day we can establish a human presence on Mars.
Inspiring, eh?
LunaNet.
So, what this video is telling us is that A, this is real, and also B, there is a lot of work to do to make, continue making this a reality, and making space networking something that is not only in the hands of NASA and a few others, but similar to the internet, something that is at disposal of humanity. And because of that, there are many things happening, many advances related to how to enhance the network from the existing, aspects. And some of you are collaborating on this, and we're super thankful for that, because this is a collective, not a single person, not a single agency. We need many people to be able to achieve this together. So things that are happening, and just to mention a few, first on the physical layer, everything so far is pretty much based on radio waves, which are fantastic, but they have limitations in terms of throughput, similar to Earth. So one of the things that are happening right now is adding, not transitioning, but adding optical links as a secondary link, just to provide additional throughput, being able to get to gigabit per second, at least on Earth vicinity, and then hundreds of megabit per second to deeper space. Many companies working on that area, and also NASA, and also not only working on creating the technology, but also working on making the technology affordable. That's super important. Second is on the link layer, a lot of work going into high-speed inter-satellite links, and that's basically to optimize the communication networks, because today the ground stations are the bottleneck, and the idea is that you should be able to communicate, through the network, and the ground station should only be another entry point. So inter-satellite links are critical for that. Then the other thing is cloudification of space. Both Amazon and Microsoft now have a ground station as a service offers, where basically you can rent a minute of a ground station to communicate to any satellite, and you pay by the minute. Beforehand, you will need to have a check with at least a few $100,000 to get access to any ground station. Now, you get one API, you have your credit card. Of course, you need to validate that you have access to that specific satellite, that you are authorized to get data from that satellite. But all you have to do is basically connect API, and you get your contact information in terms of satellite contact, and you get to go. So making also ground station accessible, and that's available today. And the last piece, which is the area that concentrates us both from IPNC perspective, from this communication we're having, or this conversation we're having here, from my company perspective, is enhancing DTN networking to ensure that there is interoperability. That's a work that some of you are going to be involved in. Scalability, to make sure that we can move from tens of nodes to hundreds and thousands of nodes. Things such as addressing schemes. Security, which is super important. That's yet for another very advanced session, how you do security in scenarios where you cannot do a handshake due to the delay. High speed DTN, I mentioned that, and then management, how you manage these network overlays, where one spacecraft might be from NASA, the forwarding relay node might be from, let's say, SPATIAM, and the ground station might be from AWS, how you manage that networking and fully interoperable environment. So there is a lot of work to do. I just encourage you to continue first playing, learning, and contributing to this. Alberto or Eric in Spatium are open to help you with any question, any comment. We have good experience with ION. We have good experience also with the D3TN implementation. We are part of IPNSIG, so we do this just for the sake of growing the baseline of interested people and people that would contribute to the advancement of space networking. I have a couple of minutes, so just want to quickly, and this is not commercial, just to give you an idea of the kind of stuff we're doing. Earlier this year, as part of SPATIAM Corporation, we collaborated with D3TN and also the European Space Agency to do the first ever commercial DTN interoperability test in space. We did it in the lower orbit with the ESA OPSAT satellite, where we were providing the cloud DTN endpoints, basically based on ION deployed on AWS, and we were able to connect them to Cloud Vision, and the use case was very nice. A cold spot, which is a node, imagine a rover on the moon that doesn't have direct internet connectivity, would communicate through DTN. So you see that there is a DTN node in the cold spot, there is a DTN node in the OPSAT satellite, a DTN node even on the dispatcher, and then our DTN node here, and connected to a Cloud Vision application. So this rover would take a picture, send that picture through the service, through DTN, and then we would be sending back the labels. So for example, saying, this is a weather alert or everything normal. And based on that, the rover could take an action, like finding shelter. That might be a good example. This was a demonstration of, first of all, the bundled protocol interoperability between the D3TN implementation and the ION implementation, and B, the capability to do an end-to-end networked application, not point-to-point, but network application that has some, usefulness in a space through DTN. So that was successful. And as I said before, very interesting things that we learned is that those contacts are very small. You're talking about, sending data in a contact window of, a couple of minutes. And the other thing we're working on is on how to manage those overlays. So it's basically how you manage the contact plans, how you manage the nodes, and basically working on a multi-agency, multi-cloud DTN network manager. So that's also that is keeping us busy at the time. As you may imagine, we collaborate very closely with the IPNSIG. We let IPNSIG users to use any of our technology, without any charge, because at the end of the day, what we want to make sure is that we're able to build the interplanetary internet together. So with that being said, that's all I had. And I think I only left 1 minute. So sorry for that, but I wanted to make sure that I covered everything this time. Thank you.
No, thank you. It was great. Appreciate you coming out.
Thank you very much.
That was a great. Thank you.
Yeah, I think you tied together a lot of the abstractions that these guys have missed out on in terms of we just threw them into ION and had them start working on the testing plan, and there's a lot of stuff that you tied together for them, I believe, in this talk that really was beneficial. So thank you very much again, Alberto.
My pleasure, Ronnie, and And folks, again, we are available here for whatever you need. Want to make sure that first of all you learn, you have fun, and second, as you get interest into this, into contributing, happy to help you to contribute.
Anybody else got any questions or comments for Alberto?
No,
Before we
just
part ways?
look forward to working
No,
with
I
you.
just want to thank Alberto for sharing his time and being so generous and sharing his knowledge with the students. I'm sure this is a project that it has legs and it's gonna be around for a long time. And you guys are the first ones to, this is the very beginnings of incredible endeavor. So I hope you
Yeah,
guys
it's exciting.
take advantage of this opportunity. Thank you again,
Fantastic.
Alberto.
Thank you. No, thank you. My pleasure. And anytime you need me or any of us, happy to be here. Thank you.
Okay, I'm going to stop the recording, and we will see you next week, next Friday in the meeting. So thank you again.
Perfect. Thank you.